Okay, hello, PyBeach. Thanks for letting me speak to you today. So most people who know me, they know me as a as a SoCal Python organizer, as you said. I'm also a PyLadies co-founder, and I've been a software developer since 2011. I wanted to give a talk about engineering rigor, not because I think I'm some sort of authority on this topic, but because I think a lot of us who are here today at PyBeach, we not only love programming, but we also want to be good software engineers, and we know that the two are very different. Even if you haven't thought that much about this topic before, I do hope that you'll find this interesting. And what I really want to do is provoke some lively discussions and ask a bunch of questions and get some ideas and horror stories from people, or success stories from people who are like-minded. So before we start, let's make sure that we're all on the same page about what I mean by engineering rigor. Here's my short list of symptoms or goals of engineering quality. So these are a bit abstract, but I'm sure if I give you like 5 seconds to think about it, you all could think of like at least one piece of software where these adjectives might not apply, right? From my own experience, once upon a time, I worked on the back-end team for a mobile app for a celebrity. And the celebrity wanted to launch this app at a certain date. And people kept coming up with all these cool features and making them more complicated, and then coming up with more features and not changing the launch date at all. So there were a lot of teams who worked really hard on this. There were back end, front end. There was marketing, media teams, streaming, payments. So we all worked really hard to try and finish all of the different pieces that we needed to put together to get this app to work. Again, the launch date was firm. So we launched. And immediately, people who were trying to use this app found all sorts of bugs, right? And of course, now we had to fix all these bugs as quickly as possible. And that was really hard because we had all worked for weeks, like overtime, right? Trying to make this app work. And now we have to deal with this, right? So in the end, actually, the celebrity had to apologize, and we retracted the app from the App Store. We had to launch a newer version, a better one, later. And that's when I learned that if your end user ends up being your QA team, that's a sign that we really could have set aside more time to maybe ensure that we had a better quality app. Right? There are more famous examples, like one time Sony sent out a PlayStation demo disc. It had this gnarly bug where if you played this demo disc but you happened to have a memory card in your slot, it would wipe your memory card. So that wasn't great. Sony had to apologize, and they issued a workaround, which was basically like, if you want to play this demo, take out your memory card first. Okay. All right. A more extreme example of software that lacked engineering rigor is the infamous Therac 25 radiation machine. So this was a machine to help cancer patients. But the software that controlled this machine was written by a developer who just kind of put together a bunch of kludges. That made it really hard for the technician to predict how much radiation was being output by the machine. And that ended up killing people, right? So that's the worst case scenario of when someone might conflate coding with software engineering, right? But let's go in the opposite direction. So here's an example that I found last year of a really great engineering excellence mindset. There was this open source contributor who noticed 500 milliseconds of latency. That's a half-second delay when he was running some automated tests. He got really curious about this because he remembered seeing something similar, in some other tests he'd run, and he dove down a few layers, deep under the stack to profile the process that he found suspicious. It was SSH. It was using a little more CPU than he thought. Eventually, he discovered there was an attempt at a backdoor being installed into a compression library called exeutils, and this would have been installed on basically any machine running, let's say, Red Hat, Debian, Arch Linux. If not for this developer, this bad patch would have allowed bad actors to log into basically millions of machines all over the world, right? So just imagine if Andres hadn't gotten curious about this bug, if he hadn't had such a good mental model of his system that he found 500 milliseconds of latency to be sus, right? Imagine if there hadn't been any automated tests for him to run, or if he hadn't been able to profile the processes that he needed to inspect. So I'm sure nobody here, but somebody out there, maybe you work with them, might say, well, we don't work on software that could kill people, like who cares? let's forget for a minute that we do respect our users, right? They're paying good American dollars to download an app for their favorite celebrity. They want to play a PlayStation game. I would still like to posit that we software engineers want to be lazy. And so I'm going to show you some graphs that can make a sort of, let's say, self-interested case for why we should care about engineering rigor and how it can make us even lazier. So some people might think of software as code that, once it's written, it's done. Like maybe in school, right? You finish a project, you turn it in, you get a grade, and then you never think about it again. But I think most developers learn very quickly that, software engineering is not just coding, and also it's ensuring that the whole system that your code runs on is sound, right? A software project, after it's delivered, it's not a strictly static artifact. Requirements can change, environments can change, your operating system might change, priorities change. So if you imagine that the right side of this graph extends out to, let's say, infinity, right, the x-axis being time, it should become apparent that 90% of the lifetime of any software is actually spent during maintenance, not in the initial development. So when we write code, we really should be optimizing for that part of code where we're doing maintenance, right? So this graph actually represents an ideal situation. Because in reality, if you deliver a project where there are bugs popping up all the time, this is going to disrupt your ability to work on the next project because that effort accumulates over time. Not to mention, like if these bugs are unexpected, now you're going to have to context switch, right? And that has its own costs. So in the long run, shipping high maintenance software, that can take up way more time. Also, it's stressful because now you've got these unexpected fires popping up all over the place. And it keeps you from working on the cool new features that people are actually asking for, right? So look at how long it takes to finish project 2 here because of all the time that's spent on project 1. So if the previous graph is the best we can hope for, like this graph 3 is pretty much a death march, right? And nobody wants to be on call all the time or working 60-hour weeks just to get all their stuff done. So if you care about your team or your own work-life balance, you should care about wanting to prevent unplanned maintenance as much as possible. So hopefully these graphs kind of convince somebody who maybe didn't care before to start caring a little bit. But how do we write software that embodies all of these qualities? So the truth is I could talk for hours or even weeks about this, right? There are so many dimensions to this topic of engineering quality. And again, I'm not an authority here. There are so many books and other resources out there that can do this topic justice way better than I ever could, especially in the time I have today. But the sheer amount of writing on this topic also shows you how prevalent it is, right? As software has been eating more of the world, it's become a lot more complex. And we're all trying to work with these layers of complexity that have built up over time. So for the 15 odd minutes I have left in this talk, I'm going to propose 3 general questions that are useful to have hanging around in the back of your mind while you're doing software development. The first one is probably familiar. It's why. So when a customer asks for a feature, asks, why do they need this? Like, what is the actual problem that they're trying to solve? Because you might be able to think of a better way to solve it and make them happy. If a teammate suggests using framework A to do a project, ask them why. Like, why is it better than not using a framework here? Or why is it better than framework B or C? Maybe they've used framework A before and it worked well and they like it. That doesn't necessarily mean that it makes sense for the context of this next project, right? And when you're adding a dependency like a framework, you really want to sit down and think through the consequences. Like, are the benefits enough to outweigh the costs of maintenance and integration and onboarding, right? You could even ask, why should we focus on engineering rigor right now? I'm going to use the example of that celebrity app. If we decided to spend all our time on this celebrity app saying we're going to build the most resilient app possible, it's going to be perfect, there are going to be no bugs whatsoever. But imagine that we'd spent so much time building out all the pieces that we need to make this, perfect, smooth running app, that by the time we launched, the celebrity was no longer famous. Like, that would be a huge fail too, right? So it's always important to think about the business impact as well. So, asking why reflects curiosity and humility. And I also think it can reveal hidden assumptions. So I'm thinking in particular of the Dunning-Kruger effect. if you're not familiar with this, the Dunning-Kruger effect is this psychological phenomenon where a novice, entering a field, they kind of know that they don't know a bunch, right? They kind of know their skill level is low. But oddly, when you get a little bit of experience and you become intermediate, you start to become overconfident. You think you know a lot more than you do, and you overestimate how much skill you actually have. Because what you don't know, and which a real expert knows, is how much there's still left to learn about that topic. They don't know what they don't know. So I think that asking why and having curiosity can expose you to these things that maybe you didn't even know you should know. So I think of it as a good guard against Dunning-Kruger. The second question reinforces this idea of thoroughly understanding the problem space or model. It also encourages short feedback loops. So if you want to build a robust system, you want to be validating it constantly, whether that's through automated tests or shipping your app into a staging environment before production, adding logging or monitoring. So getting feedback early and often allows you to quickly see if your beliefs and assumptions match reality, right? And that will reduce not only the cost of making changes, but it also reduces the risk of introducing changes. So I have here a quote from Edgar Dijkstra's essay, The Humble Programmer. And basically what he's saying is that a good mental model of a problem is critical if you want to express it correctly in code. But complexity and cognitive load, that makes it really hard to build good mental models. So anything that reduces cognitive load, whether that's keeping folder structures consistent for the team, or naming your unit tests really clearly, like you have the setup, the expected, baked into the name of the test. That makes it a lot easier for not only you in the future, but your team to build a better system because it helps them build up that mental model more easily. So this is also why code reviews are really important. They're a way to share mental models of the problem space between you and your team. And they can test whether that system is being expressed clearly enough, right, through your code. If you're reading a PR or somebody else is reading your PR and it's too complicated, maybe you guys, you need to model it a different way, or at least clearly document, why that complexity exists. The third question is key, I think, to building resilience and reliability. I think a lot of times I will see tests that only exercise the happy path through a piece of code. The test works as though there's only one possible way that this, things could happen, and that's what they test. So, one test is great. It's better than no tests, but it's not enough, right? What does your software do when it hits edge cases, like an unexpected input? What if your code depends on a server and it has an outage? Like, what if business requirements change and you have to modify some logic? How confident are you that you can modify your code so that it can handle that change without causing a regression or popping up a bug later on? If you're finding it difficult to predict how your software is going to behave, then maybe the design needs more work. But it's way easier and less risky for you to change your design before you've committed code, because once you've shipped the code, now changing that code is a lot more risky, and you're going to probably have to apply a Band-Aid instead of a proper fix for the root cause. So it's especially frustrating when you're trying to do this and you know that you could have maybe anticipated the problem if you spent a couple minutes before, early on, in the design phase, planning for these edge cases and exercising the unhappy path through your code. This will force you to design your system so you can either prevent them or handle them gracefully. Okay, so I think a lot of us here know all of this already. This is not news, right? And we all say that we value engineering rigor and we believe in quality. But if you compare our spoken beliefs against our actual behaviors in the real world, there might be some dissonance. Right? Maybe you work with people who think of software as like, that graph one, right, where you ship a thing and it's done. Maybe they haven't had, the experience of maintaining software in production for an extended period of time. Maybe your team doesn't know how to deal with how much complexity that there is in today's software. There's this book I like a lot called Driving Technical Change. In this book, the author describes a group called the uninformed, where folks just don't know what's possible or how to deal with things. They just haven't been exposed to practices. And what's nice is that all it would take is to just kind of evangelize and show them what can be done, what is possible, what exists. And you can talk to them about some of the things we've talked about today. Another common battle is this pressure to ship things as quickly as possible. There's another book I like called A Philosophy of Software Design that uses this term called tactical tornado. This is a term to describe somebody who values closing tickets fast and making the fastest change that will work. They don't dig into the root cause. They don't want to figure out how the system could be better. They just want to apply their patch, close the ticket, done, next, right? A tactical tornado, though, will gradually increase complexity and add friction over the long term. Really, they actually end up creating more tickets later on down the line. And the funny thing is that they think this is fine because they're closing a lot of tickets and they're doing it really fast. That must mean they're working hard. But are they really working on the right things? But even people who don't want to be tactical tornadoes can wind up feeling overwhelmed. If they're working on a system that is already swamped with technical debt, or they feel constant pressure from everyone around them to deliver on time, maybe they're already burnt out from dealing with so much complexity and cognitive friction day to day. So how do we overcome these things? Now, it doesn't feel that way in the moment, but I do think small steps add up over time, sort of like the opposite of technical debt. So if you follow the Boy Scout rule, which is always leave the campground better than you found it, right? For example, let's say you're editing a module and you notice that there's a variable name that's slightly inconsistent. Go ahead and make that change, assuming it's safe. Make that change, and you'll be surprised by how effective these small changes, they're very tiny, add up over time. But the key here is to make this invisible work visible to everyone. I like to say people who get paged at 3 a.m. to put out a fire, they're called heroes, right? They get a lot of glory and credit because they're doing heroic things. But nobody notices when your team has not had to wake up at 3 a.m. for a very long time, right? So you can show a number like, oh, we have 5 nines of uptime or whatever. But I would love to think of ways to show how many 3 a.m. incidents we prevented by writing good software, right? Maybe you could take an opportunity to brag about how you wrote such good tests and you have such good observability that you feel totally confident deploying on a Friday because you're not going to have to work on Saturday. Right? Automation is another great way to work with folks like the uninformed or the tactical tornadoes, because you can set up linters, formatters, tests in your CI that reduces the chance of errors. It increases consistency across the code base for everyone, and it makes it easier for everyone to do the right thing by default. So there are so many great automated code quality tools today, right? Especially in Python. And let's admit it. When a human rejects a PR, I know you're not supposed to take it personally, but it still stings a little sometimes. But when a robot gatekeeper tells you that your build is red, that's emotionally neutral, right? And the robot tells you what's wrong, it'll tell you why, and you fix it. If you can't persuade folks to want to do the right thing on their own, you might need management to mandate it on high. The book I mentioned before, Driving Technical Change, has this whole chapter on how to convince management how engineering rigor can solve their problems. A lot of it involves collecting metrics, like counting up the time spent on unplanned maintenance work, or adding up the cumulative cost of doing that. There's a good talk on YouTube called The Economics of Software Development by J.B. Rainsberger. He frames this benefit in a very management-friendly way. He says it's engineering rigor makes it easier to predict the cost of adding new features. Let's think about that. The reality is that culture is driven from the top down, and mandate from on high might be the only way to get a team to care about engineering quality. But back to laziness. I think laziness is good. I believe that we want to encourage long-term thinking. We love automation. We want to increase clarity rather than complexity. And we are user-focused. We respect the user enough to make them something that'll make them happy. My husband came up with that one. He wants you all to know this. Okay. But I'm talking about a strategic laziness. We want to focus our efforts up front in the design phase so that we can do less work later on. Because there's always going to be work to do later on. Don't worry. But to Today we write software that sits on top of so many other systems. There's already so much complexity. This is never going to be easy. But I do think that the three questions that we have here, keeping these in your back pocket will help you find your way to improving engineering quality over time. So I want to end on a horror story. So once upon a time, I fell into a trap with an LLM. Okay? I tried to refactor a Jenkins pipeline. The thing is, I never learned anything about Jenkins. I just, all I know is that I need to run this to make my build pass and run my tests. But I had to refactor this code, and I thought, well, maybe Claude would be better at it than I am. So I had Claude, do this refactor, and Claude was very helpful. Like, he spit out, a few hundred lines of code with the new pipeline. Great. But everyone knows that the first rule of using an LLM is you have to read the output. So I was like, I know this rule. I'm going to read the output. And I read it. And it looked fine. Like, I was like, there are no weird loops. Like, it seems pretty readable, actually. I think it's good to go. So I ran it. And it broke, right? So why did it broke? I looked at the output again. I looked at the error messages. I asked Claude. And I checked the docs, for Jenkins and for Groovy, which is the language that you use to run a pipeline. And it turns out there's two kinds of styles of writing Jenkins pipelines. There's declarative and scriptive. But I didn't even know, I didn't even know that was possible. So basically, I thought that the code looked okay, but I didn't even know that there were different ways to write Groovy. So I didn't recognize it when those two styles were mixed together. So now I knew because I'd read the docs. I iterated some more with Claude, and pipeline kept breaking, and I kept reading more docs. In the end, I ended up having to read all the docs anyway, right? And this whole thing took just way longer than if I had just started out that way in the first place. But the reason I tell this story is, imagine all the folks out there who think that coding is the same as software engineering, okay? And let's remember that LLMs have been trained on all the code that's on the internet. Let me repeat that. LLMs have been trained on all the code that's on the internet, okay? So, I just want to get across, like, if you want to avoid having a bad time working with LLMs, I think it's important first to read the output. Always read the output, okay? But also, it's important to know enough about the domain that you can recognize potential problems in the output that you're reading. So if you don't recognize good engineering practice from bad, then how are you going to know that the output is doing the right thing? And how are you going to avoid that graph 3 situation where you've got all these unplanned interrupts happening all the time? So, as I keep saying, I'm not an authority on this topic. I just really love talking about it. I read a lot about it. I've read a lot of stuff. Here are some recommendations. I'll post this later up on the Discord. And I love talking about it with other people. It's just a really fun topic for me, and I think it is for a lot of us here. And I would love to hear your stories about engineering rigor and ideas for how to combat all the obstacles that we face today. So yeah, please use the Discord. I organize SoCal Python with some other people. If you come up to us, we'll add you to our Slack group. I would love to spur more discussions on this topic. But at the very least, I hope I've inspired you all to be as lazy as possible. And I thank you for your time.